recording. So hi everyone. Thank you for coming. Welcome to our second webinar in our Solar Circuit 2026 series. If you're new here, we're HelioHub. We're a Discord community for undergrads and recent grads interested in heliophysics. If you're not part of the Discord yet, I'll send a link in a bit. And my name is Claudia, and Phoebe and I realized we haven't done introductions properly this summer. So just as a little quick intro, I'm a UC Berkeley student studying applied math and astrophysics, and I'm joined by my colleague Phoebe, who will introduce herself in a minute, and Dan, who usually co-hosts these webinars with us, couldn't make it today. And so this summer, we've been hosting a series of professional development workshops and webinars featuring heliophysics researchers and professionals. And today's webinar is our second in the series. If you missed any of the previous workshops or webinars, don't worry, you can always find the recordings pinned in the programming channel on our Discord. And just during the presentation, if you have any questions, feel free to put them in the chat. And we'll get to them and we'll get Lisa to answer them for you. And I'll let Phoebe introduce herself and take it away from here.
Hello, everybody. I'm Phoebe. I graduated last year from the University of Texas at Austin with a double major in physics and astronomy. And then I was able to do an internship over the summer with NASA Develop. So this summer, I'm doing another space weather internship with NASA, looking at high frequency communications for pilots. And then I'm starting my PhD this fall at Boston University in astronomy. So I'm super excited for that. But I got into this program and helping coordinate everything from being a Coffee's RU student 2 years ago at the Boulder Solar Alliance. And then Lisa here she was my mentor for that. So I'm super excited to have her back. And she taught me so much. And I would like to think that the reason I'm here is because of her. So the reason that you guys are all here is also because of her. So, okay. So to kick it all off, this spring, we just finished up our research project on HelioHub called Butterfly. And this was using AI and machine learning to build a solar cycle generator. And so by the end of this project, we wanted to kind of model our results and compare them with the current state-of-the-art technologies. So we did a score model and looked at how Butterfly compared to SARG. It's the synthetic active region generator. And so Dr. Lisa Upton here is from the Southwest Research Institute in Boulder, and she helped to develop SARG. She's a leading solar physicist and co-developer of the Advective Flux Transport model, which runs on SARG. And this is one of the world's premier models for simulating and predicting the sun's magnetic field and solar cycle. She also recently co-chaired the Solar Cycle 25 prediction panel and is the recipient of the 2025 Karen Harvey Prize. And if you guys want to look into more information on the solar cycle, you can check out her website at solarcyclescience.com. And I'm going to send that in the chat now. But she's very big in the outreach community for heliophysics and has mentored on the copies page. It said 5 students and a postdoc. I don't know if it's more than that, but I'm one. So now we can kick it off to Lisa to begin her presentation. Thank you for being here, everybody, and Lisa.
Great. Thank you so much, Phoebe. That was such an amazing introduction. I really appreciate it. It's been such a pleasure to work with you, and you've just been such a huge asset to Coffee. So I don't think I can take nearly as much credit as she gives me. She is a force all of her own. Okay, let me share my screen. You guys able to see my slide here? Good. Okay, all right, great. All right. So predicting solar cycle variability with SARG. Thank you, Phoebe, for giving an introduction to SARG. I'm going to start off by just giving you a little bit of like introduction kind of material to kind of set the stage a little bit. And so I want to start by talking about the solar activity cycle. I'm sure you guys all have a little bit of awareness about it, but just in case, we'll go over some intro stuff just to make sure. So the solar activity cycle was first discovered back in the 1800s. Samuel Heinrich Schwabe was the first astronomer to observe that the appearance of sunspots was cyclic. He started plotting the number of sunspots that were occurring each year, and he saw that there was this nice little rise and fall that developed. And as new features of the sun were discovered, it was found that they also varied along with the sunspot activity, so the solar cycle activity. And so for this reason, sunspots are now commonly accepted as our measure of the solar cycle activity. And if we look at images of the sun, there's one per year for 11, 12 years here, you can kind of see why. So the sun starts out in this very quiet state. Doesn't look like there's a whole lot going on. But as the years progress, you'll start to see active regions emerging at high latitudes. They become more frequent, and they start to progress closer and closer to the equator. So these bands move closer to the equator until they kind of join at the equator and kind of get overlapped with one another. As the cycle starts to decline, activity begins to decrease again. Once it hits the equator, activity will begin to decrease again. It'll get quiet, and little activity will appear again. And so this is what we see when we're talking about the rise and fall of the solar activity. Now, we see this in intensity images looking at the sun, but we also see that the same pattern exists and becomes much more prominent or noticeable if you actually look at images of the magnetic field. And that's what this one is showing. And you see the same kind of thing. You start with a sun that's not a whole lot going on there. There's, just kind of like this noise almost, with like speckles of blue and yellow. But at the beginning of the cycle, you'll start to see active regions emerging at high latitudes, and those latitudinal belts will start progressing closer and closer to the equator until they kind of connect with one another, and then you'll start to get the declining phase where activity will decrease and becomes a very, very quiet state again. So we've had about 25 solar cycles where you've got fairly good counts of how many active regions emerge. I'll put a little caveat on that by saying that the first 4 cycles are not quite as well observed, although we do see that rise and fall activity. If you look at the color coding here, you'll see that there's lots of missing days here, and so you'll have to take those with a grain of salt. And so when we look at this rise and fall in activity, we see that the sunspots will appear on to either side of the equator, on these bands on either side of the equator. These bands will drift closer and closer to the equator, as we just saw. And we also see that the solar cycles tend to actually overlap by about 2 to 3 years. We've got a variety of different solar cycle amplitudes. So you have some small cycles with amplitudes of about 115, but you can get as large as 300. So a small cycle would be a cycle of just over 100, and a very large cycle would be about 300. And if we're talking about the Goldilocks area, the just right cycle, the average cycle, that's going to be about the same as a solar cycle 23 with a sunspot number of about 180. Now, interestingly, when we plot these bands of activity over time, we see that they form these nice chevrons. And with this color coding, they kind of look like butterfly wings. And so that's why this plot here has actually been given the moniker of a butterfly diagram, or a butterfly plot. And this is kind of where the name for the project that Phoebe mentioned came about. So butterfly is a play on the fact that these activity belts, when plotted as a function of time, look like butterfly wings. And so using an AI to try to reproduce this behavior is kind of the concept there. Now, if we look at, I'll take a closer look at the magnetic field over time. So what we've done here is we've plotted the magnetic field at all latitudes. So on the left here, we have latitude, and on the bottom, we've got time. So if you plot the magnetic field as a function of latitude and time, we'll again see these butterfly type features appear. This one, because it's signatures of the magnetic field, is actually referred to as the magnetic butterfly diagram because it's the magnetic version of that butterfly plot. And you'll see a few things emerge, a few things that appear in that. One thing that you'll see is that there's a particular polarity that's associated with these butterfly wings, where you'll tend to have a leading polarity of one sign and a following polarity of the opposite sign. And that sign convention is opposite from one hemisphere to the next and from one solar cycle to the next. And so we'll see, one polarity here, but then for the next cycle, it's going to be the opposite polarity. And then across the hemisphere, it's going to be the opposite. This reversal, but in addition to the magnetic field that we see in the active regions, we see that there's these streams of magnetic field that are migrating to the polar region. So the top and the bottom of the plot, the North Pole and the South Pole. And we see that there's some concentration of magnetic field or flux that seems to form at the poles. And if we look closely, we notice that the polarity of that magnetic flux that's at the poles is reversing sign at about the time of solar cycle maximum. So about the time that the activity belts kind of meet at the equator is about the same time that the reversal is happening at, reversing at the poles. And so the polar fields is actually out of phase, antisymmetric with the plotting of the sunspot number. So the peak in the polar fields is at solar cycle minimum, and that reversal changes at about solar cycle maximum. Interestingly, though, the polar field strength during solar cycle minimum is correlated with the amplitude of the next cycle. And so here I've plotted the amplitude of the solar cycle as a function of time, along with the strength of the polar fields in the north and south hemisphere as a function of time. And what you see is that if you have a big difference between the North and South Pole, you'll have a large cycle. And as those polar fields become weaker and weaker, so do the amplitude or the strength of that solar cycle. The solar cycles become weaker and weaker. And so we know that the amplitude of the solar cycle, or the amplitude of the polar fields at solar cycle minimum, is a predictor for the strength of the next cycle. So to understand why, we have this phenomenological model that was created by Babcock back in 1961. And this is very soon after they started actually measuring the magnetic fields on the sun, that he came about with this idea of this concept of how the solar cycle actually works. How do you explain the sunspot cycle with these changes that we've seen? And it all starts with a magnetic field that's much like a typical bar magnet, where you have this clear North Pole and South Pole, a dipolar magnetic field emerging out of the poles. This magnetic field in the interior is actually threaded through the convection zone. The convection zone is the top 1/3 of the sun's interior. Is a turbulent convective environment. And that magnetic field in the interior is threaded through this turbulent convection zone. Now, there are flows that occur on the surface of the sun. Specifically, the differential rotation is an east-west flow, and the meridional flow is a north-south flow. And what happens is the magnetic field that's embedded in this turbulent convection zone gets wrapped around the sun by the differential rotation. So the differential rotation essentially wraps that magnetic field that's embedded in this convective zone around the sun. As that happens, the magnetic field in the interior gets stretched out. And as that stretching happens, actually that shearing effect causes the magnetic field to become stronger. And when the magnetic field gets strong enough, it will actually become buoyant and rise up through the convection zone and emerge at the surface. Now, because of this tilt that's created by the differential rotation, those active regions that emerge will also have a characteristic tilt that's associated with them, with the leading polarity of the same sign as the poles and the following polarity as an opposite sign of the poles. And so as these active regions that are sunspots emerge, they become shredded apart by turbulent convective motions that are happening in the sun. And so those magnetic fields become weak and they get spread across the sun. Opposite polarities that collide will cancel with one another. But because of this characteristic tilt in these sunspots or in the active regions, you'll tend to have a little bit of the following polarity that is residual that will actually make its way to the poles by that north-south meridional flow. And then eventually the active regions, the leading polarities of the active regions over the course of the solar cycle get closer and closer to the equator, and they cancel across the equator. But this residual following polarity flux has the opposite sign of the original dipolar magnetic field. And that's what's actually causing that reversal of the polar fields and the buildup of the new polar field that happens. And so once all that residual magnetic flux at the equatorial regions has migrated to the poles, the sun has become quiet, you'll return to this dipolar state, this very quiet state. And that residual magnetic field, that newly formed polar fields will actually become the seed for the next cycle, which will follow that same process of being wrapped, emerged, torn up, and redistributed across the sun. And that's in essence the process behind the solar activity cycle. It's how the solar dynamo operates. Now, the finer details are still an area of active study. This is a very simplified, model to kind of explain what we see, but there's a lot of nuance there that's kind of glossed over. So, one of the things about the historical solar cycles, though we have sunspot numbers going back for the last 24 solar cycles, 25 solar cycles, we only have like detailed information about the active regions for the last 100, 150 years or so, back dating back to 1880. So only about half of the solar cycles in the past do we have detailed information about the location, the area of the active regions that have emerged in those cycles. So if we want to go back further in time and try to find out what's going on in prior to 1874, we need some kind of way to simulate what might have happened in those times. And this is kind of one of the bases for creating the synthetic active region generator. And the synthetic active region generator, or SARG, is essentially a tool that's been developed to create synthetic active region cycles or catalogs that are based on all the known observed statistical properties of the active region. So all the things that we see when we look at the butterfly diagrams of the past, this rise and fall in activity, the rate that the active regions move to the equator, all these different statistical properties, the strength of the individual active regions, all the things that we can measure today. And the reason that we might want to do this is because there's value in being able to go and reconstruct the past. This gives us a mechanism by having a tool like this to create synthetic active region catalogs. We can create historical pseudomagnetic magnetograms or pictures of the magnetic field over the surface of the sun. We can create synthetic butterfly diagrams, but it also allows us to use these tools in models to create a reconstruction of the global magnetic field over multiple centuries. And using these reconstructions, we could take them even further and put them in, the photospheric magnetic field into coronal simulations and create a coronal simulation. And that gives us added context that we could then compare with historical drawings. That maybe we don't have the numbers, the specific details of the active regions, but if we can reproduce some of the historical drawings that we see, that gives us more context or insight into how the large-scale patterns of the solar cycle might have behaved in the past. This is kind of the impetus for the development of SARG, to be able to create simulations that allow us to take these steps. So we don't have the historical, the detailed active region catalog, so we can't really create those solar cycles explicitly with the active region knowledge. So we use SARG to do this. Now, the first step to creating SARG is you have to know, when does a solar cycle start? Now, as I mentioned earlier, solar cycles tend to overlap by about 2 to 3 years. And so you have to have a way to really decide when one cycle starts and one cycle ends, in terms of when you're creating these synthetic active region catalogs. David Hathaway in 1994 proposed a parametric curve fitting for the smooth sunspot number. And what he found was that you could fit the sunspot number using 4 parameters: the amplitude of the cycle, the rise time of the cycle, the asymmetry of this curve, and the start time of the curve. And the asymmetry, he found that the asymmetry parameter, C, could be fixed. And so basically, there's this characteristic asymmetry that we see. There's a rising phase and a declining phase, where the rising phase tends to be much faster than the declining phase. And that could be affixed for all cycles. Similarly, the rise time parameter, which is also known as the Waldmeier effect, could be expressed in terms of amplitude. And so what that says is that the bigger the cycle is, the faster that solar cycle will rise. And so if you take this into consideration, you can actually fit the solar cycle, do curve fitting of the solar cycle with just 2 parameters: the start time, T0, and the amplitude. And you can see that these curves do a nice job of representing those. And so what we can do is use this curve fitting technique to cleanly divide our solar cycles from one cycle to the next, to give us a start time for one cycle. Okay, so I know when one cycle starts. I also need to define the strength and the timing of each cycle. We can do that with the sunspot number. And so we've got the historical record of the sunspot number that can tell us the strength of the timing of the solar cycle. We apply the fitting function to that, which allows us to get the start time and the end time of each solar cycle. Now we need to start creating active regions for each solar cycle. Now, this gets a little complicated because traditionally, when we talk about the sunspot number, our metric for the solar cycle, the sunspot number is actually calculated by measuring the number of active regions that are on the visible side of the sun each day. And so this doesn't quite tell you the number of new active regions. It just tells you the number of active regions that are on the surface at a given moment in time. And so what we need to do is actually to convert, look at our active region catalogs and go through and identify each individual active region and count it only once. Because with sunspot number, an active region that's there today and tomorrow and the next day gets counted each of those times. And so sunspot number doesn't directly tell you how much active regions to emerge as a function of time. And so going through the historical catalogs, we've created a metric called the sunspot count. And this is the metric that actually is the number of new active regions that emerge each month. And if we look at the sunspot number and the sunspot count, there's certainly a lot of similarities. We see the general rise and fall of the solar cycle. We see this trending increase and this trending decrease in the solar cycle. There's a lot of similarities there. But there are some differences which are kind of interesting that need to be explored further. For instance, in this cycle, you see that there's kind of this jagged, it's a much stronger cycle in the sunspot count than it is with the sunspot number, and it's much more jagged than it is with the sunspot number. If we look at this cycle, we see that it actually appears fairly flat-topped, whereas its counterpart down here seems to have more of a single peak associated with it. And so there's some interesting things that arise when you start counting the sunspots in this way. But we can plot all of these points, the sunspot number, as a function of sunspot count. And so we can kind of develop this relationship. There's quite a bit of scatter, but we can develop this relationship of converting sunspot number, which is the number that we have going back in time, to this sunspot count. The next step is to use this sunspot count to also calculate how many active regions emerge as a function of time. So the way that we do that is we convert this sunspot number into a time lag, inverse it, create the inverse of sunspot count. And that actually gives you the number of days between subsequent active regions that emerge as a function of the sunspot number. And so you can plot that distribution. You can plot that distribution for each, as a function of the sunspot number, and you can see that that there's some times where you have sunspots that are lots of sunspots that are emerging per day, and you've got something every day. But you do have periods where maybe you will go 20 or 40 days, or even in solar cycle minimum, you might go 60, 80, 100 days before you'll see a sunspot. And so converting this distribution of time lag between emergences is a tool that we can use to tell us when to emerge the next active region in our sun. We can use this function, sunspot count, as a function of sunspot number. This distribution of lag times combined can be used to kind of tell us when we need to emerge the next active region in SARG. So we know when to start emerging them. We know how often to emerge them. Now we need to get into the details about the specifics of each active region that emerges. And there's several parameters that need to be described, several properties that each active region is associated with. The first and foremost, you need to know how much flux is in each active region. To get this, we've used the distribution of flux per active region as described by Munoz-Jaramillo in 2021. He looked at the distribution for several different instruments and plotted it in several different ways. For SARG, we use the Kitt-Peak Solis BMR flux log normal distribution, which is plotted here. So Kitt-Peak Solis distribution, which is plotted here. And it's a log normal distribution, which kind of makes sense. You get lots of little active regions, but as the size of the active region gets bigger and bigger, you have fewer and fewer of them. So we have the flux in the active region. Now we need to know where to emerge the active region. Well, from our butterfly diagram plots, we saw that there's this progression, this drift of these active region belts over the course of the solar cycle. And if you plot this for small, medium, large cycles and you line them up, you can actually see that this is kind of there's this standard rate of equatorward drift of the active latitudes. And so you can kind of use this to set your latitude of where you're emerging the active regions. In general, we like to simplify by saying that the longitudes of the active regions are drawn from a random uniform distribution. We know that's a little bit more complicated. We know that there are active longitudes, preferential longitudes where active regions tend to emerge. But for the purposes here, we're just going to use that random uniform distribution to select our longitude. All right, so we have a time, we have a flux, we have a location to put the active region. Now we need to determine, well, each active region is actually consists of a leading polarity and a following polarity. And so we need to find the relative locations of each polarity of the active regions. For SARG, we assume Hale's polarity. That's the polarity that we talked about when we were looking at the magnetic butterfly diagram, where it reverses from one cycle to the next. You tend to have active regions emerge, and from one hemisphere to the next, you tend to have a specific polarity associated with the active region. So we'll just use that Hale's polarity, although we know that there's about 10% of active regions that maybe are anti-Hale. We can make this assumption that in general they're Hale's polarity. The tilt of the active region, so active regions when they emerge, they have a leading polarity, tends to be closer to the equator than the following polarity. This is known as Joy's law tilt. And there's a nice paper by Munoz Jaramillo that described that showed that the active region tilt can be described with this distribution over here on the left. And so it's a very broad distribution. You can see this Gaussian here. It's a very broad distribution. And so you can use this distribution to assign the tilt of the active regions. What's the placement of the leading polarity versus the following polarity? It's represented with a Gaussian of a mean of 7.5 and a standard deviation of 22.3. But you also need to know, how far to separate them. And so we've got a plot here. This is actually goes back even further than this Upton et al. 2024 paper. And the Upton et al. 2024, so prior to that, we were using this blue distribution that dates back probably till about 10 years earlier. But in the 2024 paper, we refined this a little bit further by bending them, and we found that a nice function to describe the longitudinal separation of the active regions as a function of their size. I should also mention that the size of the active region is well correlated with the strength of the active region, the amount of flux in the active region. So larger active regions tend to have tend to be larger, so they have a larger size. So more flux equals bigger area. But this also translates to a bigger separation distance. So the bigger the size of individual polarities, the further apart that they tend to be separated. And so if we put this collection all together, we can create a realization, a picture of what a specific solar cycle might look like. And here we've used SARG to create a realization showing all 24 solar cycles with the timing, the location, and the flux for all the active regions. Here the flux and the area are indicated by the symbol, size, and color. So the larger active regions are these red active regions, and you see that they're few and far between. But as you go to cooler colors, you have much more active regions. You can see that the progression of those active regions from high latitudes to low latitudes. You can see that there's this nice there tends to be this clean gap in these simulations, and that's because we've arbitrarily or because we've defined a start time for the cycle. So we change from one cycle to the next at a fixed time. So in the actual butterfly diagram, there's a little bit more overlap between the solar cycles than you see here. And then in this realization, there are a total of 73,000 to 74,000 active regions that have emerged over this time period, with active region fluxes that range from 2 e to the 20 to 1.5 e to the 23 Maxwell, so a range of active region sizes. But if you look at this butterfly diagram, the synthetic butterfly diagram that we've created, you can kind of see a lot of similarities between it and this synthetic realization and the butterfly diagram that I showed you earlier. That's all well and good, but the true test is to actually simulate it and see what it looks like. So we've put these SARG realizations into a surface flux transport model simulation called AFT, Phoebe mentioned earlier, the Advective Flux Transport model. And basically what this does is it simulates the evolution of these active regions that SARG has created in these synthetic active region catalogs. And so you'll kind of see that process that I described earlier, where you'll have active regions starting to emerge at higher latitudes. As the cycle progresses, they start emerging closer and closer to the equator. You see that these active regions emerge and then they're shredded by the turbulent convective motions in the simulation, and they're redistributed over the sun. And we'll see that the following polarity is opposite to the poles. So here you've got yellow in the south going down to reverse the blue magnetic field, and vice versa at the north. And so taking this the next step further, we want to go back and see if we could use these synthetic active region catalogs to do a historical reconstruction of the last 24 solar cycles. And that's what I'm showing here. This is where we've taken the SARG active regions, the active regions that SARG has given us, and we put them in the surface flux transport model, and we evolved them in a continuous simulation for 24 solar cycles. And so here you can kind of see the magnetic butterfly diagram that's created, and we see a lot of similarities. You see that there's big cycles that have a lot more flux. There's weaker cycles that have less flux. We see that there's these polar streams going to the poles that are reversing the polar fields. And you see this Hales polarity kind of characteristic that we saw in the magnetic butterfly diagrams as well. From this, you can also plot the polar fields as a function of time. And that's what we've done down here at the bottom. And so these last few cycles are the ones that I showed you. These are the cycles that we actually have magnetic field measurements of the polar fields for the last 4 or 5 solar cycles. And you can kind of see that some of those same trends that we saw in the observations, where you have the big cycles, and as they decline, as the solar cycles decline, you get weaker and weaker cycles. This is a little bit forced because we did tune the model so that the polar fields would be consistent with what we would expect. But by doing this, you can see that there's this nice evolution of the polar fields over this entire period. And this is something that we don't actually have observations for. And so we're creating a picture of what the evolution of the polar fields might have looked like in the past. Now, historical reconstructions are all well and good. It's nice to look at the past and have that added context. But it's also really interesting to think towards the future. And so we can use SARG in a predictive fashion as well. So earlier in the solar cycle, one of the things that we did, this was with work that Vibhuti Kumar Jha and I did a few years back. We wanted to predict the timing of the reversal of the polar magnetic fields. And so this is our starting condition. This is the first half of solar cycle 24. And we wanted to so we created a set of 30 different SARG realizations. Well, why do you need a set of 30 different realizations? Well, SARG creates active region catalogs that vary. Each realization is based on the statistical properties, but each SARG realization is unique. If you have an active region emerging at a specific time and place in one realization, that same active region isn't going to necessarily be there for the next active region. And so though SARG captures the statistical properties of those solar cycles, each unique realization can produce a different result. And so what this allows you to do is create an ensemble of potential future states, how the future evolution might occur. And this probabilistic methodology gives you a way to quantify the uncertainties in your simulations that you've created and establish a confidence error in those. So by doing 30 different SARG realizations, you're able to capture a little bit of that stochastic nature of active region emergence that can be very significant to the reversal of the polar fields and the evolution of the solar cycle. So to do this, we have to have a basis for our realizations. If we take a look at solar cycle 25, that's plotted here in this cyan color, we find that actually bears quite a striking resemblance to solar cycle 13. And so we actually, for this particular realization, rather than using a curve fit, we actually use to the rest of the cycle. We could actually use the remainder of solar cycle 13 as to define the number of sunspots as a function of time. And so that'll be the basis of our realization. And then you can see one particular realization. The first half of it is the first half is, I think, the observations, but the last half here are the synthetic active regions. And you can see there's this nice continuity between the observations and the realization, which gives us a little bit of confidence in what we're doing with SARS, that we're creating something that is representative of what the sun might do. You see the same kind of patterns that we saw in the butterfly diagrams previously. This progression of the solar cycle, you see this bands, that there's a wide distribution of the flux emerging. You're seeing the rise and fall in activity. So there's fewer active regions. As you go to maximum, you see there's a higher density of active regions. And as you're approaching minimum, you see that decline in active region emergence. But how does it look if you actually simulate it? And that's what we've got here. So in addition to the continuity that we see if we're just plotting the active region, we see that there's actually some continuity in the butterfly diagram that's created. So prior to this white line is the observations, and after this white line are the active regions that were created by the SARG active region catalog. And it's just quite striking how well we're able to reproduce the characteristic, the quality, the appearance of the solar cycle. You see that there's the polar streams that occur here. You see that there's this mottled kind of pattern that is distinct to the magnetic butterfly diagram, and that's because you've got variation in the location and the amplitude of the solar cycles, and so you see that the mottled pattern is reproduced, and so it does quite a nice job of reproducing the evolution of the solar cycle. So let's see what it does in terms of predicting the evolution of the polar fields. So we've got the observations up to this point. From this point, we've got our simulation, so we can measure the polar fields in the past, and we can measure the polar fields of what the simulations say. And this is what's shown in these plots. So you see we've got the northern hemisphere in the plots on the left, and the southern hemisphere on the plots on the right. So if you look at the past, you see that the polar fields, these are the observations, and then these are the synthetic realizations. And this actually shows the individual tracks of each of those 30 realizations. And you can, one of the things that you might notice is that when you first start simulating into the future, there's this first 2 to 3 years where the solar cycles, all of the simulations seem to be doing the same thing. And the reason for that is that the active regions that are creating that that evolution actually already exist on the sun. Those are the active regions that emerged in the past, because it takes about 2 to 3 years for the flux, the residual flux from the active regions to make it to the poles. And so it's about 2 to 3 years after we start our simulating the synthetic active regions, that you start to see those the divergence in the polar field evolution. And we see that there's quite a bit of divergence. And this is pretty common when you're doing the time period where there's lots of active regions emerging. Any one active region can change the trajectory of your path. And so during the time of solar cycle maximum, you'll get a lot of a wide distribution of emergence. As you go to solar cycle minimum, if you start closer to solar cycle minimum, the distribution isn't quite as large. But you can take the combination, so you take the statistics of all of these, and you can find out what is the median path, what's the median trajectory of all of these different realizations. And you can use this as the basis of the timing of your reversal. And so that's when you're changing from one polarity to the next. So again, in the north and the south, they're opposite polarities, and they don't necessarily have to reverse at the same time. And so this set of simulations have the northern polar fields seem to look like they're going to reverse in about August of 2024. And the southern polar fields look like they're going to reverse in about February of 2025. So August of 2024, February of 2025 is where we make those predictions. Well, we are past those dates now, so we can actually take a look back and see how well did we do. And so these are the plots of the observations along with the simulations. And so you see that we did okay. It does look like that there was a little bit of a difference between the timing of I believe the northern, let's see, the northern polar field looked like it actually started reversing a little bit earlier. The southern polar field looks like we got that nailed pretty well. And the reason for the difference actually goes back to this variability in the observation. So you can imagine if you take this distribution and you start it at one of the downward points, or then you might get a different, that distribution will be shifted up or down compared to if you started it at the peak of one of these little divots here. And so what we find is that there's actually uncertainty that comes inherent with the starting point when you start your simulations. And so that has to be taken into consideration as well. So taking this the next step further, we are we're well into the declining phase of solar cycle 25. We expect that that's going to continue progressing well into 2030, maybe 2031. And so it's at this time where you can start looking to the next cycle. It's still a little bit premature to start predicting solar cycle 26 because, as I said, the closer you are to solar cycle maximum, the more variability, the more uncertainty that's going to be associated with your measurements. But as we get closer and closer to minimum, we'll be able to refine that even further. But we can take a look. As I said, the polar fields are the predictor of the next cycle. And so if we use the SARG simulations to simulate the rest of this solar cycle, we can get an idea of what might happen. So this is our starting point. Oh, wait, I think I've mixed it. So we've got our starting point is right here in 2026, and we've evolved, let's see here, evolved them into the future to get a sense for what the polar fields might look like. Sorry, let's see here. And Oh, sorry. And so you can evolve those into the future to get a sense of what the polar fields might look like. We're seeing some really interesting polar fields. So this is actually the observations. These are not simulations. This is observations of what the polar fields have been doing lately. And typically, you have this reversal, and then you have this gradual buildup. You might have a little bit of a lapse in the polar field strength, like we saw at the minimum of the polar fields and prior at the last reversal, you had a buildup and a slight dip. But one of the things that we're seeing with this cycle, the northern hemisphere has had a pretty large relapse that's occurred. And if we look at the magnetic butterfly diagram, we can see that that's associated with this polar stream that's here. This red polar stream has caused this dip in the active region or in the polar field evolution. And so it's really interesting to kind of, even though it's a little bit premature to start looking at the prediction for the next solar cycle, we've already got some hints that there's some unusual things happening because we're getting this unusually large relapse at the solar cycle. So it's very unusual to have such weak polar fields at this phase of the solar cycle. So if you look at the previous cycle, this is about where we were, and so we're quite a bit smaller than we were at this phase in the last cycle. So let's see here. So let's put our SARG simulations to work. And this is just one realization with SARG. Like I said, it's a little bit premature to do a whole lot of realizations, and so we just kind of threw one together relatively quickly. But we can see that the polar fields look like they're going to have a little bit of a relapse that might happen in the south. It looks like the northern polar fields might get a little bit stronger, but it doesn't look like they're going to get anywhere near as strong as they were for solar cycle 25. You can see that compared to even where we were with solar cycle 24, that they're much weaker than the polar fields were even 2 cycles ago for the weak solar cycle 24. And so what this might mean is that we might actually be heading into a weaker solar cycle 26. The sun will have a lot of work to do to see if it can recover from these relapses in the polar fields that we've seen so far. So in conclusion, SARG is a synthetic active region generator that reconstructs and that can be used to reconstruct and predict the global photospheric magnetic field. It serves as a framework to advance our understanding of the evolution of magnetic activity for both the past and the future. And the polar fields for solar cycle 26 are getting really interesting. It's unusually weak for this late in the solar cycle. We could be heading towards a weaker solar cycle 26, but it's still way too early to say. I'm looking forward to seeing the advancements of the butterfly AI work that's been going on, and possibly even maybe doing some simulations with some of those. That's what I've got for today. So I don't know if there's time for questions or comments. We can do that.
Yeah, if anybody would like to ask a couple quick questions, you can unmute or drop them in the chat.
Hi, Lisa. I had a question.
Yes, please.
It was a nice talk. I'm wondering how are you really changing the realization? Like you mentioned the time of the emergence and the location and the size and the flux, right? Or how many of the parameters are you really varying?
Yeah.
That's great.
So for, are you talking about for the historical simulations or are you talking about for the
No,
future
yeah,
simulations?
future.
Okay, so for the future simulations, you've got the time between each active region emergence. So we've got a rate of active region emergence, but there's a distribution here. So you're randomly sampling from this distribution. So
Okay.
you've got variability in the time between each active region emergence. That's based on the sunspot number and the sunspot count, right? So you can convert that to get a an estimate of when the active regions emerge, but there's a distribution here that you actually pull from.
Okay.
You pull from the distribution of fluxes, so there's variability in the amount of flux that might be in one active region to the next. There's variability across the latitudes of emergence. So this is the rate of active region emergence. There's actually a band here, and so there's you randomly sample. You take this as your base for your active region emergence, but you have a little distribution about the latitude of emergence. You randomly emerge those active regions in longitude. You've got variability associated with the specifics of each individual active region. So the tilt of the active region, it comes from a distribution that's by this comes in from this Gaussian distribution. And so there's quite a bit of parameters that get pulled from statistical distribution. And so you can get quite a bit of variability
Okay.
from one realization. And uh, that's why you see this
Yeah,
variability in the evolution of the polar fields.
nice. Thank you. Yeah. So much.
Absolutely. I see Janet's got a question. Hi, Janet.
Hey,
Thank you for coming.
it's great to see you and wonderful talk.
Yeah.
I was wondering, what about the meridional flow
Mhm.
issue and also the diffusion coefficient?
Yeah, yeah. These are part of AFT, not really necessarily SARG, but these are components of AFT. Typically in our AFT simulations, we have done simulations in the past to look at how the change in the meridional flow kind of impacts the evolution of the polar fields, and we certainly see that it can make a difference. In these simulations, we've chosen to just use use the average meridional flow. So it's a static meridional flow. It doesn't change with the solar cycle, though we know that the meridional flow does change with the solar cycle. But there is a little bit of that comes in the convection motions. The convection simulation in AFT, which is largely responsible for the diffusive action that you see in the simulation. These are time evolving convective cells, and so they evolve they've got finite lifetimes. Each convective cell has a lifetime, it's got a size, and those convective cells move with the differential rotation and the meridional flow. Now, we do a quenching function to kind of somewhat capture the meridional quenching that you see in the solar cycle variability. And so that does come in a little bit through that quenching function in the flows of the convective flows.
Right. Um, Very interesting. Also, the polar field definition. Uh,
Mhm.
you're trying to simulate, I guess, what's above 60 degrees, which is what Wilcox uses as a polar field definition.
Yeah.
Um, is that a factor, that choice?
Oh, yeah, absolutely. I don't think I show it in this particular plot. I think these are 60 degrees, but we do look at 55 degrees and above, 60 degrees and above, depending on what we're comparing with. But absolutely, it does can make a difference if you're calculating. Just for, I guess, clarification for the students here, there's lots of different ways that you can quantify the polar field strengths, and there's a hint of it right here. So one way that you can do it is by looking at the geomagnetic AA index. It's at minimum, it's kind of a proxy for the polar field strengths at solar cycle minimum. You can take the entire magnetic field over the solar disk of the surface of the sun, and you can calculate the axial dipole moment. And so that's one way of quantifying the strength of the polar fields. But this method of quantifying the strength of the polar fields doesn't tell you anything about the differences between the hemispheres. And so another way that you can quantify the strength of the polar fields is by defining a specific latitude to calculate the polar field strength. Now, historically, the Wilcox Observatory pixel was 55 degrees and above. And so a lot of the older polar field analyses use 55 degrees and above. I think with HMI, and we've moved to more often looking at 60 degrees and above, but you do have to make sure that when you're talking about the polar field evolution that you're talking about, you define what is your latitude that you're defining as your polar fields. So we do look at 55 degrees and above, and we also do look at 60 degrees and above. I don't show it in this plot, but I have other plots. I could probably track one down if you'd like to see the difference between those. That's
Great.
interesting.
Thanks for all that that work and information. It's really fantastic to see that. I appreciate your talk. Thanks.
Thank you, Janet.
There was a quick question in the chat, and then we can get to Russell.
Okay.
But Benjamin said, would you think that there's a larger cycle governing the amplitude of the individual solar cycles?
Oh, yeah, no, this is a fantastic question. And it's actually something that's actively debated in the community. So there is what appears to be an 80-year cycle. This cycle is, so the Schwabe cycle is the 11-year solar cycle, but this longer periodicity is referred to as the Gleisberg cycle. It's about an 80 to 100-year periodicity, and you can kind of see hints of what people might be thinking about. You see that there's this several cycles where you have a rise, and then you kind of have a decline, and then you kind of have a rise and a decline. What was particularly evident in the last, since the 1900s, you have this very clear rising phase and a very clear declining phase. And so this 80-year periodicity, there's debate within the community as to whether or not this is occurring because of a physical process that's happening in the sun, or if it's occurring just because of nature of the statistics. If you have a stochastic process like active region emergence, solar cycle evolution is very stochastic. This variability that occurs from one cycle to the next. You'll by default you'll generate some periodicities that kind of occur, and so there is question as to whether or not this apparent 80-year Gleisberg cycle is real or not. Depends on who you ask as to whether or not they'll say that it's a true thing, or if it's just a consequence of the statistical nature of the active region emergence. Does that answer your question?
Yes, Benjamin said thank you. And then we'll take Russell's question. And then after that, if anybody has any more questions, you can ask them on the Discord, and Lisa or somebody else can try to answer it for you. But Russell, you can go ahead.
So, thank you for the presentation. Very interesting. I was wondering if you noticed any correlation between accuracy for the historical data based on number of sunspots beforehand. Like if we were to encounter another period like the Maunder minimum, would SARG still be accurate?
Well, so SARG, you have to define, you have to give SARG a sunspot number as a function of time is the input for SARG, right? And so you have to define that. And so in the simulations, in the historical reconstruction we did, part of the reason why there's so much similarity here with the observation, the observed sunspot number evolution, is because that comes directly from the
Okay.
sunspot number, right? And we can do in SARG, we can do it by, just using the curve fitting to define how that evolves. Or you can take the actual, the profile of the sunspot number, and you can use this relationship to calculate. So that's by the rate of the emergence, which is how that comes in. But you could also use, like we did with trying to predict the reversal of the polar fields, you could use a historical cycle. And one of the nice things about this, and I think one of the reasons why SARG in AFT is able to capture some of this more detailed characteristics of the butterfly diagram that we see, is because of all of these bumps and wiggles have an impact. This variability may seem like it doesn't have a consequence, but if you do a simulation with a smooth curve versus a simulation with this month-to-month variability, you're going to get slightly different characteristics. And I think part of the reason why SARG is able to capture that so well is because in this particular set of simulations, we're incorporating this month-to-month variability that is actually a part of the solar cycle, part of the emergence of active regions, how active regions emerge on the sun.
I see. So a big reason why you might not be able to simulate cycles in the future is that you don't really know how many sunspots will happen at one time. So it's hard to have that as an input.
Yeah, but like I said, I mean, you can use if you
Right.
have an idea of how big the cycle will be, you can use a curve fitting, or you can use a historical cycle that's representative. But in terms of taking that further, but the problem is actually worse than that. You can't go past really the next solar cycle. Really, we're only able to predict the solar cycle with any kind of accuracy about 2 to 3 years in advance, and that's because of this stochastic variability that comes in from all this combination of so many different distributions, right? So you've
Right.
got a distribution of the time of emergence. You've got the distributions in the Joy's law of tilt. You've got the distribution in the number of flux, the amount of flux that emerges in one active region to the next. And so if I were to just do a single simulation and say that I wanted to predict what the polar field strength would be at, in 2028, if I just did one single simulation, I might get a simulation that's down here, or I might get a simulation that's up here. And you can see that spans the whole entire strength of the polar field, right? Now,
Right.
fortunately, as you get closer to cycle minimum, a lot of this variability comes from all those parameters associated with the active region emergence, right? The time between emergences, the amount of flux, the tilt. When you go closer and closer to solar cycle minimum, you have fewer and fewer active regions emerge. The sunspot number is declining, less active regions emerge. Less active regions emerging equates to a tighter distribution across the simulations, right? And so, when you get, 5 years ahead of solar cycle minimum, you can make this set of you can make a set of simulations that's going to say, okay, well, I've got this range of distributions and this is my average. But to get something that's meaningful, that might actually be representative of what's going to happen on the sun, you really need to get about 2 to 3 years, before the minimum, to really make to refine that accuracy to a point where you're actually saying something meaningful about what might happen for the solar cycle, which is why I'm very cagey about even showing a simulation this early in the solar cycle, right? Because
Right. Yeah.
this is just one simulation. Maybe the next simulation, it goes way up here, and so yeah, we get a simulation that reverses, or there's a simulation. This one, has this downturn that happens here. This downturn is clearly a consequence of the active regions, is a consequence of the active regions that SARG has this particular realization, right? As I said, the first couple of years here, that's going to happen. That's on the sun already. But these out here, there's going to be a broad range. And so I would not at this point say for sure that the solar cycle's 26 is going to be weak. But I will say that the sun's got to work hard to keep it, to make it strong if it's going to do so, right? And we've only got a few years left for it to do that. So it'll be very interesting to watch what happens in the sun in the next couple of years to see how do these polar fields continue to evolve.
Okay, great. Thank you very much.
Yeah, absolutely. Thank you all so much. Such great questions. And do please feel free to ping me in the Discord. Just do at I think, what am I listed in the Discord? Just feel free
You
to
have
at me.
flowers. I don't know what your
I'm
username.
Flowers, yes. I'm the
Uh,
one that's Flowers. Yes, feel free to, but I think if you do
as
at
Lisa.
Lisa, if you do at Lisa, it may make it to me. But yeah, feel free to ping me in the Discord. I'm happy to answer any follow-up questions that you might have.